So good afternoon. I'm Dimitris, PhD student from the University of Patras, Greece, and I work with Dr. Gouliatos, Dr. Lander, and Dr. Kodopoulos on force-free magnetospheres, force-free magnetospheric configuration and highly magnetized neutron stars. So what I'm going to present you today is a solution and properties of these magnetospheric configurations, and I will attempt to make a connection between this model and observations of magnetars and the intermittent pulsars. So I will pass this. Okay, so if a system in equilibrium has zero Lorentz force, then it obeys at this equation, and we can say that the magnetosphere that comes from this equation is a force-free magnetosphere. We can see the first illustration of a relativistically rotating force-free neutron star at the left, where the region of the closed magnetic field lines is down there, and the rest of the magnetic lines cross the light cylinder smoothly and extend to infinity. Here, the current sheet is placed at the equatorial plate, and its start is at the light cylinder, which is at r equal to 1. After that, I think subsequent work has been shown that the current sheet isn't mandatory to be placed at this at the light cylinder, but it can move to the interior. Okay, so what we will see is a model that the current sheet can move to the interior, and the closed magnetic field lines can carry a colloidal current sheet, which is produced from a toroidal magnetic field. So, as both the radiative profile and the spin down rate are determined by the magnetosphere of pulsar, any variation of the magnetic field can affect them both. This occurred by twisting the magnetic field in lines through sharing of their foot points. A lot of work at astrophysical literature has been done. Particular focuses to the magnetoflares and outbursts. And the main idea is that a magnetosphere can accommodate a maximum amount of twist, beyond of which it becomes unstable and releases its energy through an explosive manner, possibly through ideal or resistive instabilities. This model is for non-rotating magnetospheres. However, many other simulations have shown that relativistic effects cannot be neglected if the twist is strong enough. Twisting a magnetosphere can be happened through shearing of the stellar crust driven by internal magnetic stresses in the star, or either through shearing of the stellar crust or currents flowing from the crust to the magnetosphere. So what we are actually doing is that we consider an axially symmetric aligned rotating system. We solve this partial elliptical differential equation, which is the so-called Pulsar equation, and by expressing the magnetic field in terms of scalar function psi, and I, where psi is the magnetic flux function, which should be constant across field line, and I is the colloidal current that we apply at the region of the closed magnetic field lines, and is produced from a toroidal field at the same region of the closed magnetic field lines. Then we try to construct the magnetosphere of the CKF model, Kodopoulos, Karanas, and Penn. Alpha and n are numerical parameters, and psi 0 is the value of the magnetic flux along across the last closed magnetic field line, which you can see here in red. Here is the light cylinder, and it starts from the current sheet, which starts from the light cylinder. So this picture is a picture that has no colloidal current distribution at the region of the closed magnetic field lines, and only the essential current distribution at the region of the open field lines, in order to have this smooth crossing of the open field lines. Now we will increase the parameter alpha which means that we will apply linear current distribution, which means that n is equal to 1, and by increasing this linear current distribution, which means that we increase A, we see that the previous closed magnetic line, for example, A, is now open and smoothly crosses the light cylinder. What we see is that there's a limiting value of A, which the current sheet should be shifted to the interior. Because if it doesn't, then the magnetosphere will have an unphysical and unacceptable structure. I mean that in this region, magnetosphere starts to be prone to reconnection. And we will have something like magnetic islands, magnetic lines that do not start from the stellar surface and they do not end at the stellar surface. So if we displace the current sheet to the interior, then the magnetic field should have this acceptable form. And if we increase the current, then we have to make more drastic displacements of the current sheet to the interior. Now, if we focus on this plot, we will see the magnetic energy of the region of the closed magnetic field lines as a function of the parameter alpha. What is of interest is that there are magnetospheres with different degrees of twist that may have similar or the same magnetic energies, like for a magnetosphere with a colloidal current in the region of the closed magnetic field lines equals to, for A equals to 2 and A equals to 3.5, these two regions have different twist but the same magnetic energy. I will try to give an explanation at the end of this presentation for this plot. Now, if we apply non-linear current distribution at the region of the closed magnetic field lines with, for example, for n equals to 1.5 and n equals to 2, then we would see that the magnetosphere starts to inflate and more previously closed magnetic field lines become open and cross the light cylinder. If we look, for example, here, we will see that if the current distribution is big enough, then we have to displace the current sheet drastically to the interior, and it will until it approximates the stellar surface. So there is almost no closed field line region, and all the magnetic lines are radial and approaches the split monopole solution. Now, if we try to make some plots about the spin down luminosity and the polar cap according to the twist we apply to the magnetospheres, we will see that both of them increase. The polar cap becomes bigger, and the spin down luminosity becomes increases if more twist is added. We can see the same at these two diagrams where the polar cap interacts. Here we can see the polar cap as a function of the displacement of the current sheet, and here the energy loses as a function of the displacement of the current sheet. What I should say here is that this model needs it would be better if the model was a 3D model, a time-dependent model, because energy losses are not so much accurate in this model. Also, if we see the polar cap, we will see that it increases over a value of 45, 50 degrees. That's a huge polar cap, and this is because the light cylinder, this model, is only 10 times far away from the 10 stellar radius. It should be, which I think it's like a millisecond pulsar. If we want to be more accurate, we should have numerical simulations with the light cylinder to be placed 100 or more times away from the stellar surface, which is computationally very, very expensive. So if we how to make a connection between this model and the magnetars and intermittent pulsars, then we will see that this model may give some predictions about glitches. For example, at this neutron star, glitch events were followed by intermittent and rotating radio transient type emissions. So a glitch provides sudden twist in the magnetosphere. The twist has three effects. First, it produces currents at the region of the closed magnetic field lines. Second, the displacement of the current sheet and the enlargement of the polar caps. When the current at the region of the closed lines increases, then we have an increase of the amount of the plasma in the closed lines, and some particles may bombard the surface of the star and lead to X-ray emission. Of course, there's an interface between the closed and open field lines because the enlargement of the polar cap leads to gaps and likely to pair creation. Also, there are some pulsars you see here, intermittent pulsars, that exhibit modding and new leak behavior. They switch between an on and an off state. So if we would like to make a connection, this shouldn't be here, but somewhere there, but okay. If we would like to make a connection between the magnetic energy as a function of A and the observations of this specific intermittent pulsar, then we will see that maybe the two states, the off state and the on state of the pulsar, have a connection with the lowly twisted magnetosphere and the highly one magnetosphere. So, as a conclusion, we can say that the increase of the current of the closed magnetic lines above the minimum value is supported by a shift of the current shift to the interior. The magnetosphere becomes more twisted, the field more radial, and the spin down rate higher as the current increases. The twist cannot be indefinitely increased as a finite amount of shearing leads to radial field lines, and the pulsar can switch between twisted and untwisted states. Thank you.
Okay, so when you increase the twist, of course, the twist requires more current, right? But your field is also more radial. Your pair opacity drops. So how do you reconcile that? You may not be able to satisfy the current to increase the twist.
So the question is that if I increase the twist,
yes, the field is more radial.
Yeah.
The pair opacity to make supply the plasma to make the field more radial is not be possible, right? So
yeah, maybe, but if that happens when the current sheet is approximately near to the surface of the star, so there is a small region of closed magnetic field lines, and all the other magnetic lines are open. I don't know about I don't think that I can have a prediction about the plasma creation here, because the polar cap is really huge in this.
Could be the twist itself is the polar.
It becomes radial at large distances from the neutron star. There are.
It becomes.
It does not affect the magnetic field close to the neutrons.
It does affect that.
No.
Like trying to.
I run hundreds of such simulations. I know what I'm talking about.
Okay. Yeah.
I'm using the old Yanis's code, the for solution of pulsar equation.
Yes, the solution.
Are you using Yanis?
Yes.
Yanis's code. So you're matching solution inside and outside the light cylinder. How do you solve the pulsar equation?
There are two regions, yes. There are two regions. The one region.
Who knows the code? It is
higher of the code.
Will you
Yes.
Okay, I got the code.
So are you using the same approach as Yanis?
Yes. Through successful relaxation, that's the method that I use to solve the Pulsar equation, and there are two regions. This region
Okay,
beyond the right cylinder and other.
I developed a much more efficient approach. You could have
Ah.
used it and run your code like hundreds of times faster.
Okay.
So just look at, you definitely read Kyle Parfres and Andrei Goloborodov's paper.
Mm.
So just what happens if you increase the twist? And so just in this approach, because you're solving an analytical problem, you're basically stabilizing the magnetosphere, preventing it from reconnecting and releasing the twist by extending the current shift closer to the neutron star. What happens in reality, because like Kyle's suggest you do if you use a different approach, is that the outer parts of the closed magnetic neurons reconnect, release the twist, and then the current shift extends almost up to the light cylinder. That's, I'm afraid, that is a consequence. Because I adopted this problem many years ago, but I never published. So just I know the details.
Okay.